Morning, everyone. All right, how are we doing? Questions while we wait a few moments? Morning, everyone. Come on in. Today we're going to finish Taylor-Maclaurin series. Maybe do a bit of linear algebra review. That's the plan. Date for the midterm, we haven't decided yet. We will have a look at binomial series as well today. And what is the question asking? Radius of convergence. I think it's clear that the radius of convergence is going to be 4. Radius is 4. The midterm is going to be a timed midterm, as is suggested on the course outline. What we're looking at right now is a 1.5 hour midterm. So as you know, you're going to be given twice that plus 30 minutes. So you'll be given 3.5 hours. That's what we're looking at. Adamar is asking how I can tell just by looking. Experience. If you've done many of these, you see what's happening. You see what's happening. Let's do it. We're looking for interval of convergence or radius of convergence, right? I mean, if you have one, then you're going to have the other, essentially. Limit as k goes to infinity. K plus 2 here, right? Aiden, I cannot guarantee that. All right, so there it is, the usual, right? I mean, we're looking for, the question was radius of convergence. Here, this is going to give us the interval of convergence. And then from there, we'll easily find the radius. Right, let's cancel some stuff. First of all, these things don't matter because we're an absolute value. X to the k minus x minus 4 to the k. This crosses out. This 4 to the k crosses out, leaving us with what? We still have an x minus 4 on top, a k plus 1 to the 1/2, a 4 on the bottom, and a k plus 2 to the 1/2. This is constant. Pull out a k from here, pull out a k from there. So square root of k times 1 plus 1 over k to the 1/2. Square root of k. So we can cancel these. As k goes to infinity, 1 over k goes to 0, 2 over k goes to 0, so the whole thing goes to x minus 4 over 4 in absolute value. And for convergence, you need this to be less than 1. So x minus 4 in absolute value should be 4, and there is your radius of convergence. Right? Because this means that x minus 4 has to be between 4 and -4, or x is between 0 and 8. So if you didn't notice it from here, you can certainly see it here. Is there an abbreviation for writing limit k goes to infinity? Wow. I want to say it's short enough, right? It already is an abbreviation because it's really a limit. So we already shortened it down there. All right, there it is. Well, why don't we get back into the swing of things by considering a few questions before we move on to other things? Well, maybe it's best that we move on right now, and we'll come back. Chloe's asking a good question here. Do we need to check the ends? Do we need to check the endpoints if we're just asked about the radius? Of course, the answer is no, because whether or not these points are included, the radius itself will remain the same. All right. So, I mean, what have we been doing? We have been looking at Taylor and Maclaurin series, and we've been saying that f of x as a Taylor series is the nth derivative evaluated at c over n factorial x minus c to the n. Right, this is Taylor series in general. And, you know, I mean, we derived this business and everything was nice, but it's all a lie. What am I talking about? This equality isn't it isn't necessarily. A function is not always equal to its Taylor series. The Taylor series doesn't always converge to the function. We waved our hands of this, and I kind of suggested that it was, but it isn't. So what happens? When is it? Right? Of course, as usual, this being a series, you could always add the first n terms. Right? As you usually do, right? This is a typical way of approximating. So this may be viewed as an approximation to what the series converges to. Let me introduce some notation here. This is actually going to be a polynomial, right, of degree big N. So this is known as the Taylor polynomial of degree N. So let's call it T big N. This first part so that's known as the Taylor polynomial of degree N. And the rest is known as the remainder. Now, it's easy to see right? So what are we saying? In other words, we're saying the function is the Taylor polynomial plus a remainder. So if you bring this to the other side, right? That's why it's called the remainder, because it's the difference, it's what's left. And in order for the Taylor polynomial to converge to the function, need the remainder to go to 0. Right? This is going to be the error now. So the error is the absolute value of the remainder. So in order for the Taylor polynomial to converge to the function, we need the remainder to go to 0. So there's actually a condition for the function to be equal to the Taylor series. We need the remainder to go to 0. Now, this remainder is itself an infinite series. But luckily, we have a very nice closed form that comes to us from Lagrange, which is really an application of the mean value theorem. So here is the Lagrange remainder theorem. If your function, no, not your function, if the nth plus 1 derivative is continuous on an interval containing x and c, containing x and c, there exists a z between x and c such that your remainder term or n of x is equal to, right? So this big sum is equal to the n plus 1 derivative evaluated at z over n plus 1 factorial x minus a, x minus c to the n plus 1. Containing, yes. Sorry about that. Look, let's not worry about the midterm for now. As soon as we have decided on something, we'll let you know. You can expect to have at least 10 days, if not 2 weeks notice. So, yeah. All right. It should. Thank you. We mean the n plus 1 derivative here. N plus 1 derivative. So if the n plus 1 derivative is continuous, then your remainder has this form for some z between x and c. It's really an application of the mean value theorem. I'm offering it without proof, but if you remember the mean value theorem, right, you have this point existing in the interval. That's what's happening. So if we go back to this business, right, your Taylor polynomial is going to converge to the function as long as the remainder converges to 0. And if you look at this, right, I mean, this n plus 1 factorial here, you know how large that is. That's very, very, very large. So in order for this not to converge to 0, your function has to behave very badly. this is going to go to 0 for almost all functions. There are very few functions for which this fails to go to 0. So even though Taylor series don't all converge to the original function, it's very rare that they don't. The simple example, and it's an example the book will have you do, I think the counter example, I wish I had taken it down now. I want to say, not 100% sure here, e to the negative 1 over x squared for x not equal to 0, and 0 for x equal to 0. First of all, it's not clear that this is even continuous. You can show that it's continuous, you can show that it's differentiable, and in fact, it's infinitely differentiable, right? So I mean, first of all, for the Taylor series to even exist, your function needs to be infinitely differentiable. So here, if you calculate the Maclaurin series, you can show that the Maclaurin series is 0. So the Maclaurin series converges to 0, but yeah. It's an example in the book. The book has you do it as an exercise. So it's one of the exercises in the back of the section. It's a nice exercise. Go ahead and try it. What we're going to do is the following. But if it doesn't, wait. The conclusion is that R of x rarely does not converge to 0. Exactly that. And if it does not converge to 0, then the Taylor series is not equal to f of x. Exactly that. Is Rn the limit or just the function? Rn is the remainder. So Rn is this infinite sum from n plus 1 to infinity, but this is the Lagrange form of the remainder. Lagrange remainder theorem is telling you that this is equal to that for some value of z. That is unknown. Let's illustrate with this. And let me first discuss the issue. Well, let me leave that there for a moment. What's the issue? Suppose you wanted to find the Taylor series of this function. Does Rn need to be summed, or is it just in that form, right? I mean, that's the thing. Rn is really the sum from n plus 1 to infinity. Right? This is really what Rn is. But the Lagrange remainder theorem is telling you that it has this nice closed form. That's what we're saying. Back to this. Did you work out the Taylor series for this already? Can everybody do that? That's a nice midterm question. And it'll show us the issue with this problem. Right? First of all, ln x, if we consider f of x is ln x, the derivative is 1 over x, which you're going to rewrite as 1 over 1 plus x minus 1. Oh, no. I mean, it's the, and it is approaching infinity, right? This is Rn, and what I've erased before, if Rn goes to 0. Well, I mean, the original question is x ln x. I'm saying I'm going to start with ln x. I'm starting with ln x, I get this. And so ln x itself is going to be the antiderivative of this, which is -1 to the n, x minus 1 to the n plus 1 over n plus 1 plus an arbitrary constant. And when you plug in x equals 1, which is obviously in the interval of convergence, you get 0 for that, 0 for this. So C is 0. In other words, ln x is equal to that, or let me start this at 1 instead. -1 to the n plus 1, x minus 1 to the n over n. Right? Marie, it's exactly what you're suggesting. And I've just then pulled out the -1 to the n. It was 4x ln x. I am suggesting that we're going to treat the ln x first, and then we'll multiply by x. Right? We have the Maclaurin series, the Taylor series around 1 for ln x. Well, I mean, you're suggesting magic because you know what the magic is, right? Of course, multiplying by x isn't going to do it. There it is. Right? If you multiply by x, since you've got an x minus 1 here, it's incompatible. So you're not going to multiply by x. You're going to multiply by x minus 1 plus 1. And that's going to be x minus 1 ln x plus ln x. And consequently, when you multiply this by x minus 1, you get an x minus 1 to the n plus 1, and then you have to add the original ln x. There it is. But now you have two things, so you want to merge them together. Let's make a change of variables here. So this becomes the sum from 2 to infinity. Negative 1 to the n, x minus 1 to the n over n minus 1 plus and now let me write out the first term and combine everything. So when n is 1, you have x minus 1 plus the sum starting at 2. Well, let's say this. Negative 1 to the n, x minus 1 to the n over n minus 1 plus minus 1 to the n plus 1, x minus 1 to the n over n. Let me pull out a negative 1 to the n, maybe an x minus 1 to the n as well, leaving us with 1 over n minus 1 minus 1 over n, and we're almost done. Blah, 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 you know what to do there. And we get negative 1 to the n, x minus 1 to the n over n minus 1 times n. There is your Taylor series. These started at different values. So I wrote the n equals 1 case down, and then this starts at 2. Can you do it the normal way, finding the derivatives and so on? Well, I mean, I'll invite you to do that. Do it. Why did we do this? Well, I mean, you wanted the series for x ln x. But if you just multiply this by x on both sides, I mean, you'll get the x ln x on the left, it's all good, but now you have x times x minus 1 to the n, and that's no good. You want powers of x minus 1. So a very nice trick is to add a 0, minus 1 plus 1, and we're all good. All right. What do I want to bring your attention to? Remember that the original question was, well, you say dark magic, and I understand what you mean. However, I wouldn't call it dark magic. I would call it tricks that you're picking up in this class, right? Multiplying by 1, adding 0. We've used this trick over and over and over again in calculus. What I want to bring your attention to is that recall that x was between 1/2 and 3/2. So if you take x to be, let's say, 1/2 and plug it into this is going to be negative 1/2 to the n, which you could rewrite as negative 1 to the n, 1/2 to the n, and then the negative 1s to the n cancel. Where does the x minus 1 in front come from to the left of the board? This is the n equals 1 term. Right? So what am I saying? If x is anything, in fact, less than 1, then the negatives cancel and you just get a positive term, a positive series here. And remember, we want to approximate. So now you have to approximate this positive series, and there's no hope of using the alternating series test result. And we're in trouble. This is where, so first of all, you understand that you're in trouble now. You're in trouble as far as this question is concerned if you just blindly found the Taylor series. This was not the question, right? I'm just pointing out that issues arise here. The original question was asking for the Taylor polynomial of degree 3. And that's why they wanted you to do that, because they knew there were issues. So let's find the Taylor polynomial of degree 3. This will find the usual way. Nobody is catching why we're in trouble. If x is 1/2, plug in 1/2 into this. So here you get negative 1/2. And this whole thing and negative 1 to the n times negative 1 to the n is negative 1 to the 2n, which is always 1. So these cancel out. And now if you wanted to approximate, right, because this would have been 1/2 ln of 1/2. If you wanted to approximate that, you'd have to approximate this. But how do you approximate that? How do you approximate that? That's the problem. It's approximating this, which is an issue, because it's not alternating. It's not alternating, so you cannot apply that alternating series test business that we were doing. Exactly. I mean, there are other techniques that you could use to approximate, but I mean, the easy way is the alternating series test. Tiffany and somebody else is suggesting the integral. Absolutely, absolutely. You could approximate using the integral. But then you'd have to show, I mean, that this kind of thing is decreasing and so on, and what if it wasn't, right? All I'm saying is the typical way to approximate is alternating series. There are other techniques, but they could all fail. They could all fail. That's what I'm saying. Luckily, the Lagrange remainder gives us another way to approximate. And let's do it. Let's see the Taylor remainder at work. These people have been blocked. So f of x was x ln x. Let us look at f of 1. You know, the usual thing. F of 1 is 0. The derivative, which is ln x plus 1. Derivative at 1 is 1. Second derivative is 1 over x. Second derivative at 1 is 1 again. Third derivative is minus 1 over x squared. Third derivative at 1 is minus 1. And let's go with a fourth derivative, which is 2 over x cubed. Sorry about that. Right, so what are we saying? T3, which which is f of 1, f prime of 1 over 1 factorial x minus 1 plus second derivative at 1 over 2 factorial x minus 1 squared plus third derivative at 1 over 3 factorial x minus 1 cubed. Right, so what is that? This is 0 plus 1 over x minus 1, 1/2 x minus 1 squared, and finally 1 over 6 x minus 1 cubed. That is your Taylor polynomial of degree 3. Now, what was the question asking? Estimate the accuracy in using this to approximate right? So your function x log x minus this is equal to your remainder, R3. Well, that's your, we need to be given an upper bound. You don't need to be given an upper bound. You need to give me an upper bound. And that's where the remainder comes in, right? The difference between these two things is the remainder. And now Lagrange remainder theorem tells us that this is the fourth derivative evaluated at some value z over 4 factorial x minus 1 to the 4th. Louis is asking, why did we find T3 the long way? Couldn't we have used what we had before? We could not, because it's actually not T3 that's of tremendous importance. You could have found T3 using what you had before. That's not an issue. It's really the fourth derivative that's important. And you don't know what the fourth derivative is just by knowing, well, you don't know the fourth derivative in general just by knowing the Taylor series. Right, so that's what the Taylor remainder tells us. For some z between x and 1. And now you see we were given that x is somewhere in this interval. So now we have to ask the question, well, actually, I've left it as fourth derivative, but you know what the fourth derivative is. So this is really 2 over z cubed over 4 factorial x minus 1 to the 4, or x minus 1 to the 4 over, I want to say 12 z cubed. So you see, your error is bounded by this. And now the question arises, How large is that? Right, so before we had a series for which we could not use the alternating series test to approximate, but now we have an upper bound regardless. And this idea of Lagrange remainder always works, alternating series test or not. Right, so this difference is equal to this. For some z between x and 1. So how large does this get? That's the real question. How large does this get? And x minus 1 in absolute value is less than or equal to 1/2. Right? If you subtract 1 from both sides, so x minus 1 in absolute value is less than 1/2. So here, x minus 1 in absolute value, that's going to be less than 1/2. So this is less than or equal to 1 over 1/2 to the 4. The 12 is constant. And what about z cubed? What about 1 over z cubed? How large does this get? Z is some number between x and 1. So z lives in this interval. So z has to be in this interval as well. And if you concentrate on this interval, on this inequality, and you cross multiply, 1 over z is less than or equal to 2. And consequently, 1 over z cubed is going to be less than or equal to 8. Cube both sides. So maximum value, as Charles pointed out, occurs when z is 1/2, and this becomes 8. So this is, you can replace the 1 over z cubed with an 8. And what do we get? 1 over 24? 1 over 24. So we have a nice upper bound of 1 over 24. The error is at most 1 over 24 if you use T3 to approximate x ln x for any value of x in this interval. It's very nice. It's very, very nice. Yeah. Why is z between 1/2 and 3/2? Well, z is between x and 1. So whatever x is, z is going to be between x and 1. So x can be anything in here. We don't know. But if x is any number, right? I mean, x is going to be at, it's possibly 1/2, which would mean that z is between 1/2 and 1. And why is z upper bound 3/2 and not 1? Well, it depends what x is. If x is 3/2, which it could be, then z is between 1 and 3/2. We just don't know. Here we're given a range for x. Oftentimes you're given an actual value of x. In this particular question, you were given a range. How do we get the 2/z³ in the numerator? Well, that's where the fourth derivative, right? It's the fourth derivative. We had calculated the fourth derivative originally. Would we have to check for both cases of x? Here, I'm suggesting that we did the worst case scenario. Worst case is this. If x was actually given, then you might have a better approximation. Was z between x and 1 given the initial problem? It was not. It was not. You knew it by the Lagrange remainder theorem. Why did we pick z 1/z less than or z bigger than 1/2? Well, that's so we get an upper bound on 1/z³, which is what we were looking for. Well, I mean, again, we knew this. All right. Let's move on. Always asking why we found the power series to begin with, only to show you that it wasn't a good idea to find it. A lot of people have been asking about the binomial theorem, and I know that it looks overwhelming. There's nothing going on there. What does the binomial theorem say? For a real number k, 1 plus x to the k is equal to the sum from 0 to infinity. What is that? K choose n, x to the n. Is that right? That's exactly right. And what is this? This is shorthand notation for the following. Right, I mean, binomial distribution, a very important probability distribution. Let's prove it. Let's prove it to show you that there's nothing daunting about this theorem. And how are we going to prove it? What is going on here? So this symbol here pronounced, if you will, K choose n is really K factorial over n factorial K minus n factorial, right? And you can cancel these, and that just gives you K times K minus 1 times K minus 2 all the way to K minus n plus 1. The point being that this is really only defined for integer values of K, where K is bigger than n, but this is now defined always. So this could be viewed as shorthand notation for exactly that. You don't have to view this in a stats setting. It makes no difference. What are we saying? If you take a step back, we're saying that the Maclaurin series for this function is that. That's all we're saying. The Maclaurin series for this function is this. That's all that's happening here. Let's prove it. How do you find the Maclaurin series? You know exactly how to find the Maclaurin series. We're going to do it the long way. Your function is 0. The derivative, you know what the derivative of this is. It's K 1 plus x to the K minus 1. Derivative at 0 is K. Second derivative, second derivative at 0. And you keep going until you see a pattern. Third derivative, third derivative at 0. I think we see what's happening, right? The next derivative, you're going to have a K, K minus 1, K minus 2, K minus 3, and so on and so on. Put everything together. F of x is f of 0. F prime is 0 over 1 factorial x. Second derivative at 0 over 2 factorial x squared. And so on and so on. In our case, 1 plus x to the k, f of 0 is 1, derivative at 0 over 1 factorial x, second derivative over 2 factorial x squared, third derivative over 3 factorial. All right, we're back. Very good. Questions here? Let's, before we leave this business, why don't we do a few examples of stuff to illustrate the power of Taylor-Maclaurin series. Consider this nice question. Right? Consider that function x over 1 plus x squared. The question is asking for the 101st derivative at 0. You have options. You could differentiate this 101 times and then plug in 0. Assuming no mistakes were made, you'd be good to go. Seems like a lot of work. Surely there must be an easier way. There is. And the idea is to notice that in a Maclaurin series, you have all the derivatives of the function at 0. Right? In a Maclaurin series, f of 0, f prime of 0 over 1 factorial, and so on, all the way to the 101st derivative at 0 over 101 factorial, x to the 101, and so on, right? You see that the 101st derivative at 0 is right here. It's a beautiful observation, no? So if we find the Maclaurin series for the function, and let me start with 1 over 1 plus x squared. You know why. Don't ask me why. You know exactly why. And so now if you multiply the whole thing, Alessandra is asking if there's a trick to know when to use the Lagrange remainder theorem to approximate stuff. let's say as a last resort, if it's, I didn't see what Jeremy says. I hope he asked why, but then he shouldn't have removed it. Anyways, yeah. So last resort is what I would say if your series isn't alternating Lagrange remainder. Let's say that. Right, so we have this is equal to that, multiply everything by x. You knew where we were headed with that. X to the 2n plus 1. Right, so we have the Maclaurin series for that. And all we need to do is look at the coefficient of x to the 101. When n is 50, what happens when n is 50? We have negative 1 to the 50, x to the 101. But in your general Maclaurin series, this is the 101st derivative at 0 over 101 factorial x to the 101. Right, so I mean, if you forget this, and you see that f to the 101 is 101 factorial. Where did that plus 1 come from? Lushal, I'm sure you know where that plus 1 came from. Rick is asking if the binomial theorem holds for non-integer values of k. It actually does. The theorem was for any real number k. What if they ask for the 100th derivative? Indeed. What if they ask for the 100th derivative? Somebody want to address that? Well, I think we had already answered it. There is no term with x to the 100, so the coefficient is 0. So the 100th derivative must be 0. Marie, why 2n plus 1 and not 2n? 2n was for the 1, we have x. You are allowed to compare with other sigmas because the Maclaurin series is unique, right? So the coefficients of the similar powers of x have to be the same. The last step, 101st derivative, right? Cancel the x's and just bring this to the other side. 101st derivative at 0 has to be 101 factorial. Find the sum. You know what that is. Does anybody see it? Exactly that. You just isolated the coefficients. I'm saying, right, I mean, normally you wouldn't even have the x to the 101 here. I just threw it in for convenience to illustrate what's happening, but these are the coefficients of x to the 101. Here, the coefficient of x to the 101 is negative 1 to the 50. And your general Maclaurin series, the coefficient of x to the 101 is this. Solve for that. Very nice. Very nice. This is e to the 3 over 5. Very nice. Louis has given us the answer here. How did we find the sum? We recalled that e to the x has Maclaurin series, x to the n over n factorial. And this is true for all n, for all x. The interval of convergence is all real numbers. You can plug in any real number you want, and in particular, if x is 3 over 5, e to the 3 over 5 is 3 over 5 to the n over n factorial, which is exactly what you have right there. If f of x is 1 plus x cubed to the 30, what is the 58th derivative at 0? And what about the 60th derivative at 0? Should all Maclaurin series for elementary functions be instantly recognizable to us? Again, my point is for you not to learn them by heart, but have done them so often that they become second nature, especially exponential function, e to the x, sine x, and cos. So these three you should essentially know by heart. All right. Well, you're looking at this and you're thinking to yourself, binomial theorem, right? 1 plus x to the 30 is 30 choose n, x to the n. And by the way, I did not tell you for what values of x. Yeah. It's yeah. So Yeah, I hadn't did I mention the interval convergence for x in the binomial theorem? I think I forgot. Binomial theorem. This was valid for x between -1 and 1. Sorry about that. Completely forgot. At 58 of 0 and the 60th derivative at 0. Yep. Right, so binomial theorem is valid in this interval. And yeah, so we have this. And here, if you replace x with x cubed, of course, you know what's going to happen, right? 30, choose n. X cubed to the n or x to the 3n. What are we looking for? 58th derivative. So what is the coefficient of x to the 58th? Right, we have an x to the 57, x to the 60, but no 58. The coefficient is 0, and thus the derivative is 0. What about the 60th derivative? This happens when is the power of x 60, when n is 20, so coefficient of x to the 60 here we have 30 choose 20, and in the regular Maclaurin series, coefficient of x to the 60 is the 60th derivative at 0 over 60 factorial. It's easy to see. It's easy to see that the 60th derivative at 0 is 30 choose 20 times 60 factorial. Choose 20, which is 30 factorial over 20 factorial times 10 factorial times 60 factorial. There it is. What if n is greater than 30? Absolutely. Well, I mean, you've understood what this really means. Which is why right, if n is bigger than 30, 30 choose n, which is really 30 factorial over n factorial 30 minus n factorial. This really becomes, you can cancel these for values less than 30, and this becomes 30 times 29 all the way to 30 minus n plus 1. And that's what that becomes. Yeah, that's not how that works, right? The 30 factorial and 20 factorial, these do cancel, but they don't leave you with 10 factorial. Instead, they leave you with 21 times 22 all the way to 30. Jeremy's asking where the 10 factorial came from. It's from our definition, right? We said n choose k is n factorial over k factorial n minus k factorial. So it comes from the minus k. But n starts at 0, so doesn't the 30 factorial cancel out? And in the n equals 0 case, yes. And the coefficient is 1. How are we doing here? Well, you'll be happy to know that this is the end of series. Dragged on for way too long already. Why does 58 not work? Well, there is no value of n, which makes this 58. So there is no 58. So the coefficient of x to the 58 is 0. What's next? We're going to do, I was planning to do a review of linear algebra today. That didn't happen. It's not going to be a big review because I know you know linear algebra. You're all experts in linear algebra. The only thing we're going to review are lines and planes, just so that everybody's on the same page. If you feel that you need a review of linear algebra, a review of vectors, dot product, cross product, you could do that today, tomorrow. Essentially, we're moving on to chapter 12, but I'm only going to do the section on lines and planes. So everything everything that comes before, I'm going to assume you know. In fact, I'm assuming you know lines and planes as well. We're just going to do a few examples just to get us back into the swing of things and quickly move on to extending calculus to higher dimensions. That is going to be our goal for the rest of the semester. So differentiation, well, limits, continuity, differentiation in higher dimensions, functions of several variables. And then once that has been mastered, we're going to do integration in several variables. So that's the plan for the rest of the semester. We're going to start that on Thursday. So please review vectors, dot product, and cross product if you feel you need to. We will do parametric functions and polar coordinates. We are doing partial derivative. That is in the context of extending differentiation to higher derivative to higher dimensions. So the answer, what answer were we looking for? No. The answer, we had two questions, right? The 58th derivative at 0. Here we concluded it was 0 because we didn't have an x to the 58. And when we looked at the coefficient of x to the 60, that occurs when n is 20. The coefficient is 30, choose 20. And the coefficient of the regular Maclaurin series corresponding to the coefficient of x to the 60 is this. So bring this to the other side. That is your answer. That's why I'm answering Louis' question here. That's why we just use this as shorthand notation for n times n minus 1 times n minus 2 all the way to n minus k plus 1 over k factorial. This expression doesn't make sense for k larger than n, but this one does. So if k is larger than n, you want to think of it this way. Is the midterm only on series? We're still debating that. It's going to depend on when the midterm actually is. If it's sooner, it's going to be only on series. If it's later, there'll be more material. All right, questions? Anybody? Somebody's asking where the 60 factorial comes from. It comes from the coefficient. This is the coefficient of x to the 60. In the regular Maclaurin series, this is the coefficient of x to the 60 in this Maclaurin series. By uniqueness of Maclaurin series, they have to be the same. All right. What will the final term be in k choose n? Where k is bigger than n? Exactly this, but with the k and n interchanged. There actually isn't a final term, right? Because it keeps on going forever. If n is a natural number, then this is going to end. The Maclaurin series will be a finite series. It's a nice observation there. Where does the 10 factorial come from? From the definition of this. All right. Thank you all for coming, folks. I will see you on Thursday. Review some linear algebra if you need to, and we'll discuss that at that point. You guys have a good one. See you then.